Good evening, everyone. Myself, Sana Sheikh, a second year PhD student at IIT Bombay, and I am a TA of the NPTEL course named Symmetry, Stereochemistry and Applications. And the course instructor is Professor Anshuman Roy Chaudhary from IISER Mohali. This is the last week session, a live session, and this is the 12th week. So, in every live session on Monday from 7 to 9 p.m., we are discussing the previous year assignment question of this course, which is named as Symmetry, Stereochemistry, and Applications. So, this one is the last session. Today, we are going to discuss the uh, we are going to discuss the lattice and their based questions, previous year questions. So here we are going to start from today's session. So this is a week 12 question from last year. So the question number 1 is, which among the following is not a Brevis lattice and why? What will be the answer? If you will learn the crystal system, you will find that there are 7 crystal systems, and in 7 crystal systems there are 14 Brevis lattice. There are 7 crystal systems and 14 Brevis lattice. And if we will talk about the Brevis lattice, I will write here system. System 14 Brevis lattice. Okay, 14 Brevis lattice. Okay. So what is Brevis lattice? So Brevis lattice is nothing but any of 14 possibility of three-dimensional configuration of point group which is mentioned in 7 crystal system. So we will discuss here in this question which of among the following is not a Brevis lattice. So this is a three-dimensional system. So all of you know that. I hope all of you know that there are 7 crystal system. First one is cubic, correct? I'm writing here the crystal system, cubic, then rhombohedral, then hexagonal, and here monoclinic, orthorhombic, tetragonal is given. Cubic I have already written. So 3, 3, 6 and 1 is remaining here. What's remaining? That is triclinic. Triclinic. Correct? Triclinic. So these are 7 crystal systems present in lattice. There are 7 crystal systems. So while we are talking about the Brevis lattice, so in cubic lattice we have 3 Brevis lattice. First one is primitive, then face centered, F, and I means body centered, right? So PFI means primitive, face centered, and body centered. All 3 are present in cubic lattice. So what is primitive? I will draw here. I'm drawing here cube. Okay. So in primitive cell, all the corners of the cube have atoms. The atoms occupied all the corners of the lattice cube unit cell. This is called unit cell also. So there are 8 atoms which is occupied all the corners of the cube, which is called as primitive unit cell. Primitive unit cell. What about the face center? In face center cubic cell, all the 8 atoms are occupied the center corner of the uh, cell, unit cell, like primitive cell only. But the only difference is that the other atom will be present on the face of each lattice side. Each lattice side will have the atom, face centered atom, which is called a face centered cubic lattice. You can see here, and this is back side here. So in face centered cubic lattice, we have the atom present on every face of the cube, all face of the cube. While talking about the body center cubic lattice, I will discuss here. It will look like similar like primitive cell, but the only difference will be there. The atom, one more atom will be present in the center of the primitive cell, that is called the body center lattice, body center cubic cell. So this is a body center cubic cell. So all of you are clear with the primitive, face centered and body center lattice, I hope. So now let's talk about the Brevis lattice present in these systems. So as I told you, cubic system have 3 Brevis lattice, that is primitive, face center and body center. The rhombohedral have only primitive face lattice. Primitive face lattice. While talking about the hexagonal, hexagonal also have only primitive face, primitive lattice, Brevis lattice, primitive P, and triclinic also have only primitive lattice, primitive lattice. While in case of the monoclinic, there are 2 systems are present. First one is cubic and the second one is primitive. So both cubic and primitive are Brevis lattice in monoclinic, and orthorhombic have all 4 types of unit cell, like face centered, primitive, body centered, and A. All 4 type of lattice. While talking about the tetragonal, we have primitive and body centered lattice only. Primitive and body centered lattice. So according to the question is that which among the following is not a Brevis lattice and why? So we have seen here in 4 options, monoclinic have both the lattice P and C, as I told you, cubic and primitive. So this is the correct Brevis lattice, right? So this is not the correct option here. Then the option B contains orthorhombic, which have all the unit cells, that is face centered, primitive, body centered, and A also. So this is also not the correct answer for this one, because they have asked for not a Brevis lattice. So this is also a Brevis lattice. Monoclinic is also a Brevis lattice. While talking about the cubic, so cubic also have primitive face centered and body centered cubic, body centered lattice. So this is also the Brevis lattice option. Now let's talk about the tetragonal. So as I told you, tetragonal have only these 2 lattice, that is primitive and body centered. These 2 lattice are Brevis lattice, not face center. Face center is not present in tetragonal. Okay. Tetragonal crystal system has a defining symmetry of a single four-fold rotation axis, and a face-centered tetragonal lattice doesn't have the symmetry, so it belongs to the tetragonal system, but there is no face-centered lattice is present as a Brevis lattice in this tetragonal system. So the correct answer is uh, tetragonal F. According to the question, this is the correct answer. Tetragonal face centered is not a Brevis lattice because it doesn't have a symmetry. So I hope this question is clear to you. We will move to the next question now. Here the question is given here. Point out 5 differences between molecular symmetry and crystallographic symmetry. So as all of you know that molecular symmetry is the symmetry which we are calculating for molecules, and it's passing through the molecules. But while talking about the crystallographic symmetry, it might be or it might not be passing through the molecules, and it's talking about the crystal system, not a molecule. So that's a main major difference here. So we will discuss the 5 differences here. First, I will give example for molecular symmetry. Suppose we have water molecule, correct? We have water molecule. So here, when we will pass the plane, it will pass through the oxygen, and we will get the sigma V plane. Sigma V plane. So yeah, as I told you, molecular symmetry is the symmetry element in molecular symmetry is passing through the molecules or atoms of the molecules. But in case of the crystallographic, we don't have these type of conditions. It could be passed through the molecule, or it could be passed through the space near the molecule. So here in molecular symmetry, we are writing the plane of symmetry denote with sigma. Plane of symmetry is denoted by sigma v. Suppose this is a vertical plane, so it will be denoted by sigma v. So basically, plane of symmetry in molecular symmetry is denoted by only sigma. Sigma h and sigma v both are the different conditions, horizontal and vertical planes. So here in crystallographic symmetry, what will happen here? Suppose this we have molecule or lattice, and we are passing plane. What we will get here? This one, correct? This one. So these are two mirror images of each other. So in crystallographic symmetry, the plane is denoted by M, mirror. It's denoted by M. This is the first difference. We can say here, this is the first difference. Or second, because it could be passing through a space around the molecule, and the symmetry element molecular symmetry should be passed through the molecule, and in crystallographic symmetry it could be passed through space also. And second difference is sigma plane is denoted by M, that is mirror plane. And the second difference is that in crystallographic symmetry, suppose we have any molecule and we are passing it through the two-fold of axis. Suppose here we are passing axis of symmetry C2, correct? C2. So we will get the indistinguishable image of the molecule. So here instead of C2, we are writing 2. 2 means two-fold of symmetry, like this one. If you will rotate this molecule like this one, you will get this as a product. So this is the two-fold of axis. two-fold of axis. So the second difference is two-fold of axis is denoted by 2 here. Now the third difference is that in molecular symmetry, the Cn axis is denoted like this one, Cn, and n is equal to n is equal to 1, 2, 3, 4, 5, 6, etc. Infinity, till infinity we can say. Till infinity. While in case of the crystallographic symmetry, number of that is fold of symmetry axis is given by n is equal to 1, 2. We are denote directly n here Cn, and in this crystallographic symmetry we are directly writing n. As I told you, for C2 we are writing 2. So Cn axis, for Cn axis we are writing n, and n is equal to 1, 2, 3, 4, 6 only. So why not 5 or why not 7, 8 or infinite? So I'm not going to discuss these things in detail. You can find these things in a book which is named as F.A. Cotton, chapter 11. You can get details from that book. So here I'm just pointing out the difference between the molecular symmetry and crystallographic symmetry. Okay. So you can find out this from F.A. Cotton book, chapter number 11. Okay. Now let's talk about the other differences. The other difference is that in molecular symmetry we have sigma V, sigma H, sigma H, sigma D, right? Dihedral plane, correct? But in crystallographic symmetry, everything is denoted by M. M means mirror, and MT translational, and M perpendicular, this way, M perpendicular, or ML, we also called it ML. So this is another difference. The next difference is that in a symmetric element, the next difference is that here we have Sn axis in molecular symmetry. This is molecular symmetry. This is crystallographic symmetry, CS. Okay, Sn, where Sn is rotation reflection axis, whereas in case of the crystallographic symmetry we are writing here n n bar, because n we are writing uh, for axis of rotation also. So n bar means it's a rotation inversion. Rotation inversion. Rotation and inversion. Correct? Yeah. and here it is rotation reflection. Rotation reflection. So this is the another difference between molecular symmetry and crystallographic symmetry. And here in molecular symmetry we have the center of inversion I, and in crystallographic symmetry also we have center of inversion I, which is denoted by I. Here we have identity element E, and in this case also we have identity element E. Now, talking about the more point group in the crystallographic symmetry, we have a glide plane. We called a glide plane in crystallographic symmetry. Glide plane. You can learn all these terms and topic in detail by videos available on YouTube by Professor Anshuman Roy Chaudhary, and you can study in detail these points. Because this is a live session, I am going to find out the different questions regarding your doubts, and I am going to solve those questions only. I cannot go in details. Glide planes are nothing but the mirror plane plus translation. Okay, the mirror plane plus transition. One more point group is present here. One more point group is present in crystallographic symmetry, which is known as Screeve axis. Screeve axis. The Screeve axis and its example are explained in detail on YouTube video. So you can find it from there. So I am writing here just name Screeve axis, which is present only in crystallographic symmetry. So this is a rotation transition axis again. Rotational transitional. So these are the few difference between the molecular symmetry and crystallographic symmetry, which is present in different molecules and lattice respectively. So I hope this question is also clear to you. So can we move to the next question? So this is the third question. Here they have mentioned that justify or rectify the statement all chiral space groups are non-central symmetric, but all non-central symmetric space groups are not chiral. So the sentence is mentioned here. First, you should know that what is space groups. So space groups are derived from the point group of the crystallographic symmetry. So there are space group, two types of space groups. I will write here. Total 240 space groups are present in lattice chemistry. So here I am talking about the space group. First of all, okay. So space groups are further divided into two types. First one is cubic. or we can call it centric. I will write here centric. It will be better to understand. Centric. Then the second one is non-centric. Non-centric. Okay. Centric point group or space group contains I, that is inversion center. Inversion center. And non-centric space group doesn't have space center. Center of inversion. Doesn't have center of inversion. So, which central group which contains center of inversion have different point groups like P2M, P2 by M, that is second fold axis, and mirror plane, PMM, P1, etc. There are many space groups present in this type. While in the second case, where there is no I or center of inversion is present and non-centric molecule contains P1, P2, P2, PM, PC, PM, PC, etc. space groups. So, while talking about the non-centric space group, there are further two types. They are divided into two types. First one is chiral and the second one is non-achiral or not a chiral molecule, we can say here. So, I am writing here the first case is chiral, and this one is achiral. Second one is achiral. Chiral molecule do not have mirror plane. As I told you, chiral molecule do not have mirror plane. M. While achiral molecule have mirror plane. Can have mirror plane. Which is denoted by M. So in chiral molecule, there are different point groups comes under this group, that is P1, P2, C2, P1, P2, C2, P4, etc. etc. While in this case, the point group space group like PM, PC, CM, etc. comes in this molecule. So the question was that all chiral space groups are non-centrosymmetric, but all non-centrosymmetric space groups are not a chiral. So the first sentence we will see here, all chiral space groups are non-symmetric. So you can see the chiral point group are comes under the subgroup of non-centric molecule or non-centrosymmetric molecule. So the chiral molecule will always be comes under a non-centrosymmetric molecule because it doesn't have a center of inversion. All chiral molecule doesn't have a center of inversion, that's why it will comes under non-centrosymmetric molecule. But while talking about the second sentence, here it is that all non-centrosymmetric space groups are not chiral because non-centrosymmetric groups are divided into two different types. That means it contains two types of molecule, which is chiral and achiral both. So if center of inversion is absent, that doesn't mean it could go under chiral molecule because it can contain a mirror plane. So if it will contain mirror plane, it will become achiral. So that's why the all non-centrosymmetric molecule are not chiral, but all chiral molecule are centrosymmetric molecule because chiral is a subpart of non-centrosymmetric molecule, but non-centrosymmetric is a parent chain of chiral and achiral molecule. So I hope this is also clear to you. If any doubt, any question regarding this is there, you can ask me on YouTube also, and we can discuss in next class. Might next class might not be there, so we can ask on discuss on YouTube. Okay, I hope this is also clear to you. So the next question is given here, the question number 4. Write down the coordinates in terms of x, y, z for symmetry elements. So here we have given the few coordinates we have to write in the form of x, y, z symmetric element. So while talking about the axis, so here you can see that this is given as a axis. These two C, M, 2, these are axis. So the first, we will take the first one, 2, 1 parallel to y axis. 2, 1 means this is the second pole of axis 1, 2, 1 axis parallel to the y axis. While talking about the coordinates in terms of x, y, z, we know that for second fold of axis we are writing here, if it is parallel to x-axis, we are writing x, y, z in terms of x, y, z equivalent points. So we will write here, because it's parallel to x-axis, so we will write x, y bar and z bar this way, correct? So this is a way of writing equivalent coordinate in xyz form, xyz term. So while we have the second fold of axis on y-axis parallel to y-axis, here I am writing parallel to y-axis, then what, how we will write here, xyz equivalence x, y and z, correct? Similarly, if we have second fold of axis parallel to z axis, then we will write x, y, z. Here x, y and z bar, x bar, y bar and z. Same in a similar manner, if we are writing 2, 1 axis, 2, 1 parallel to x axis, x-axis, what we will write? Because we have 2, 1, so here in terms of x, y, z, we will write here, because it's parallel to x-axis, x plus half. It will become x plus half, and y and z. Correct? This is the x, y, z coordinate of the first molecule, first question. First example is given here. So this is the answer for the first one. Okay. Now the next is given here, C perpendicular to y-axis. If we will talk about the perpendicular axis, perpendicular to axis, then we know that if A is there, that means it is the x-axis, x coordinate, and B is there, that means y coordinate. Here it is given C coordinate, that means it is the z coordinate. C means z. So either we can write here C, or we can write z. Both are same. Which is perpendicular to y-axis. Okay. Sorry, in this question they have mentioned C is a perpendicular to y-axis. That means here we have to write y, because they have mentioned perpendicular to y-axis. So if perpendicular to y-axis, C point coordinate is there, that means in terms of x, y, z coordinate, we will write here x, y, z, and x, y bar, and z. This will be the answer for second one. This one. But okay. Now let's talk about the third one. Third one is given that M is perpendicular to Z axis. Okay, M is perpendicular to Z axis. So M is a mirror plane which is perpendicular to Z axis is given here. So I will write here M, that is mirror plane, perpendicular to Z axis. So in terms of x, y, z coordinate, we will write here x, y, z, x, y, and z bar. So this is the answer for the third one, third sub question. The fourth and last one is given here, twofold axis parallel to the x-axis. So as I told you here, this is the twofold axis parallel to the x-axis, the very first example. This one. So this is the correct answer for the fourth one. If twofold axis is parallel to the x-axis, we will write in terms of x, y, z coordinate, x, comma, y bar, comma, y, z bar. So this is the answer for these questions. So I hope all of you are got the correct answer for all the questions. So in today's lecture, what we have done the question based on symmetric element and lattice. So in today's lecture, I will give a little summary for today's lecture. Today's live session, which is done on 24th April 2023, week 12. In this course, we have discussed the last week session of the live session of NPTEL course, and in this course, we have discussed the crystallographic point group, symmetry point group, lattice and space, and introduction of Brevis lattice, etc. So here in this session we have discussed the previous year assignment question, which contains four different types of questions. In question number 1, we have discussed that the which is not a Brevis lattice and which one is a Brevis lattice. So here we have done that monoclinic have there are we have discussed here that in lattice system there are 7 crystal systems. Those 7 crystal systems are monoclinic, orthorhombic, cubic, tetragonal, rhombohedral, hexagonal, and triclinic. Among these 7 crystal systems, we have the from these 7 crystal systems we have 14 Brevis lattice. Brevis lattice are given here, 14 Brevis lattice. So in monoclinic system we have 2 Brevis lattice, that is cubic and primitive. In orthorhombic system, we have face-centered cubic lattice, primitive Brevis lattice, body-centered Brevis lattice, and a Brevis lattice. Also, so here we have all types of Brevis lattice present in this molecule. And while talking about the here we have discussed that in monoclinic we have side center. This C is a side center unit cell and primitive unit cell. Side center and primitive unit cell. Now, in case of cubic lattice, we have primitive face-centered and body-centered Brevis lattice present. Now, in case of the tetragonal, we have the we don't have face-centered cubic lattice. Instead of that, we have primitive and body-centered cubic lattice. Why we don't have the face-centered cubic lattice? Because we don't have symmetry here. Because a tetragonal crystal system has a defining symmetry of a single four-fold rotation axis, and a face-centered tetragonal lattice does have this symmetry. So it must belong to the tetragonal system, but there is no face-centered Brevis lattice in the tetragonal system. So in case of the rhombohedral, we have primitive unit cell, and hexagonal and triclinic also have a primitive Brevis lattice only. So according to the option and question, we can say here they have asked the question that which is not a Brevis lattice. So all the monoclinic, orthorhombic, and cubic I, all these three have a Brevis lattice, but tetragonal F is not a Brevis lattice. Is not a Brevis lattice. So the correct answer is tetragonal F. So then we have moved to the next question, where we have discussed the difference between the symmetric molecular symmetry and crystallographic symmetry. So here we have done the difference, five difference between the molecular symmetry and crystallographic symmetry. So as we have talked about the molecular symmetry, in molecular symmetry, point group or element, symmetry element pass through the molecule itself. Mo- Symmetry, sorry. In molecular symmetry, the symmetry element is passed through the atom of the molecule or molecule itself. So this is the sigma v, and here we have rotation axis also C2 like this. While in case of the crystallographic symmetry, the symmetry element could also pass through the space near the lattice or molecule present. So the molecule contains a lattice structure, and the crystallographic symmetry, the symmetry element will pass through the lattice, that is space near the molecule. So in molecular symmetry, we have denote the rotation axis by C2, while in case of the crystallographic symmetry, it is denoted by 2 only, directly 2. We are writing 2. And in case of molecular symmetry, the plane of symmetry is denoted by sigma plane, sigma, while in case of crystallographic symmetry, it is denoted by M, mirror plane. And if we'll talk about the Cn axis in symmetric element, molecular symmetry, we have n equal to 1, 2, 3, 4, 5, 6, 7, 8, infinity, by infinity. But in case of this crystallographic symmetry, here the rotation axis is denoted by n. So n is written here, n, n bar, because it's a rotation axis. Sorry, not n bar. N bar is for rotation inversion axis. So n is equal to 1, 2, 3, 1, 2, 3, 4, 6, 7, 6 only. So in the crystallographic symmetry, we have n equal to 1, 2, 3, 4, 6 only. The reason for not 5 and 7, 8 and infinity is given in a book F.A. Cotton, chapter number 11. You can check from that chapter. So this is the another difference here. And in molecular symmetry, the SN axis is given here for rotation and reflection. SN axis is present in molecular symmetry for rotation and reflection, whereas in case of crystallographic symmetry, there is n bar, which is showing the rotation and inversion of the axis molecule, rotation and inversion of the molecule. And here in symmetry, molecular symmetry, I is in inversion center, and in case of the crystallographic symmetry also, I is showing the inversion center. Here E is present, that is identity element, and in this case also E is present as a identity element. Another difference in crystallographic symmetry is that it contains a glide plane. Glide plane means it's a mirror image plus transi- mirror plane plus transition. So here one more axis is present, that is called as skew axis. Skew axis is nothing but the rotation and a transition. So if you want to learn these glide plane and skew axis in detail, you can check the YouTube videos which has which talk about these two terms, glide plane and skew axis, in detail with examples. So here we have discussed the more than 5 differences between the molecular symmetry and crystallographic symmetry. So this is also clear to you. Now the third question was that justify or rectify the statement all chiral space groups are non-centrosymmetric, but all non-centrosymmetric space groups are not chiral. So here we have space group. So in this lattice chemistry we have 240 space groups. 240 space groups. So among the 240 space groups, we have divided these space groups into two types. The one is centric and the second one is non-centric. Centric contains center of inversion and non-centric contains no center of inversion. So in centric point group, we are having some center of the molecule which giving our different point groups. In non-centric point group, space group, we don't have center of inversion. That's why this non-centric space group is further divided into two types. That is chiral, and the other one is achiral. So chiral space group contains do not contains M, that is mirror plane, but the achiral space group contains M plane, that is mirror plane. So because chiral space group doesn't have mirror plane, so it comes under different space group like P1, P2, C2, or P4, P4, P222, etc. While achiral molecule comes under PM, PC, CM, PMM, PCA2, PNA2, etc. space group. So, because the question first sentence was that all chiral space groups are non-centrosymmetric. So, you can see from here, chiral uh, chiral space groups are always comes under non-centrosymmetric type. But the second statement was that non-centrosymmetric space groups are not chiral. So, all non-centrosymmetric space groups are not chiral because it could be achiral also. Because chiral and achiral, both types of space groups are comes under non-centrosymmetric molecule. Non-centrosymmetric molecule is there, that means there is no center of inversion, but that doesn't mean it couldn't have the center, could not have any plane of symmetry. If plane of symmetry is present, that means it is achiral, and if it absents, that means it is chiral. So that's why all the chiral space groups are non-centrosymmetric, but all non-centrosymmetric space groups are not a chiral. So I hope this is also clear to you. So this statement is clear to you, and we have justified and rectified this statement as well. So the next question was here, question number 4. Write down the coordinates in terms of x, y, z for the symmetry elements. So here we have to write the coordinates in terms of x, y, z. So for A, that is 2, 1 parallel to y axis, we have written here 2, 1. If 2, 1 is parallel to, sorry, we have written here for x axis. I made mistake here. If 2, 1 is parallel to y axis, in terms of xyz plane, xyz coordinate, The answer will be x, comma, y plus half, y plus half, comma, z. So this is the answer for first question. In terms of x, y, z, 2, 1 is parallel to y axis. We will write this way: x, comma, y plus half, comma, z. This is the answer for this one: x bar and z bar. Okay. This is the answer for first one. And the second question was there: C is perpendicular to y axis. So we have seen here, if C is perpendicular to y axis, that time we have in terms of x, y, z coordinate, we have to write x, comma, y bar, comma, z. So this is the answer for this second question. And for third one, it is given here M is perpendicular to z axis. That is mirror plane perpendicular to z axis. So, mirror plane perpendicular to z axis, we will write in terms of x, y, z coordinate. So, x, y, z bar. So, this is the answer for third one. And the fourth one is given here: two-fold axis parallel to x axis. So, two-fold axis parallel to x axis will be written in terms of x, y, z coordinate: x, comma, y bar, comma, z bar. That means y and z is going to change and x will remain as it is. If you have to imagine in 3D, then it will be more clear to you. So, in 3D, what happened? We have this type of axis. Correct? This is z, x, and y. So we will discuss one by one. If 2, 1 axis is parallel to y axis, 2, 1 means it's the half. So on parallel to y axis, this is parallel to y axis. This is the y axis. So what will change? Which coordinate will change in this case? So only x and z will change, and y will remain as it is. And because it's a 2, 1 axis, that's why we have to write here 2 half, y plus half. Right. Now let's talk about the third one. M is perpendicular to z axis. That means mirror plane perpendicular to z axis. So perpendicular to z axis, that means it will cut z axis. So that means x and y will remain as it is. Only z axis is going to change. So here we have z axis. Right. It will change. Now while talking about the fourth one, two-fold axis parallel to x axis. So here you can see that two-fold axis, that means a C2 axis which is parallel to x axis. If it will be parallel to x axis, it will cut only yz plane. The only yz will going to change. That's why we have written here x, comma, y bar and z bar. So you can imagine in 3D also, and try by yourself. And if you are not getting the correct answer or any difficulty, we can discuss on YouTube also. So I hope today's live session is clear to you. We have discussed 4 questions in today's live session. All the best for your exam. Thank you so much for your kind attention. Thank you.